Hi, my name is Aubrey Beal. I'm a professor in the Electrical and Computer Engineering Department at the University of Alabama in Huntsville. And I'd like to take a few minutes to talk to you about some kind of low-cost homebrew electronics that you can use to do DNA multiplication. That's kind of a project that we have going in conjunction with our biology department at UAH. And what's fun is, it just uses some Arduinos and some simple, like, handful of components to do DNA multiplication. And, I want you to keep in mind that, with the same components, you could probably build a robot or many other things. And I think the overarching kind of point I'd like to make is it's a fun, exciting time to get into electronics. The barrier to entry is very low as far as like money is concerned, and there's a lot of resources online. So, for a few $100s even, you can have a nearly world-class lab, in your garage or your bedroom where you can build things like DNA multipliers. So I hope you find it interesting, and I think stick around. I think at the very end I'm going to have like a small demo where I'll kind of show, how there's like a closed loop system doing heating and cooling more or less. So how would you go about finding if DNA is present in a sample in general? Well, I think it can be a little bit of a hard problem, and it's incredible that it works at all. One popular way of doing this is called the polymerase chain reaction, sometimes called PCR. And I would like to eventually show you how electrical engineering can play a role in building a PCR machine to basically test samples to see if a type of DNA is present, even RNA if it's present, and that can lead doctors and researchers, biologists, to learn if someone's infected with a virus or someone was present at a crime scene or things like that. So you might recognize this shape. This shape is a double helix, right? This shape right here. And this double helix shape is DNA. And this DNA contains genetic material. That's these little boxes in the middle, right? And what will happen is we can put this DNA into a solution, but generally we might not have very much DNA. So if we wanted to test to see if DNA is present, then there's not enough material for us to really know. So what we would need to do is amplify the DNA. So how could we amplify DNA? Well, the way that works, and the simple answer is a lot of chemistry, basically, and I am not an expert in chemistry. I know a little bit about electrical engineering. So we won't look at the chemistry, but what I want to show you is if you have the right chemistry and the right solution, you can put this DNA in that solution, and what you'll find is if you control the temperature with that solution over time, so we'll call this temperature, and this is in time, and this is just a rough kind of cartoon of what might physically be happening. It might be at room temperature at first when you take your sample, right? So it's just at some line, and you're going to ramp the temperature up to some kind of high temperature. When you're at this high temperature, if you have the right chemical solution, the DNA that's in that solution will tend to break apart. And one helix might break into this one side and another side. And the genetic material that's inside of the helix will be broken apart with it. And inside the solution is basically more chemicals that will attach themselves to either side. And that reaction is going to happen at a different temperature. So maybe this solution needs to be brought down to a new temperature. And if you were to, what I'm going to call iterate, or just do this process over and over and over again, what happens? Well, you start with just one strand of DNA, right? And that one strand, double helix, it breaks into two, right? And then it's copied, those two copies get copied, and then you get four. And then those four copies get doubled again, and you get 8. As you can see, in a very short amount of time, we'll have a lot of copies of the DNA if this all works perfectly. And this is called exponential growth. So we'll exponentially have more and more DNA present in our sample. Eventually, even if we have a very small amount of DNA at the beginning, we'll have a very large amount of DNA after, let's say, about 45 minutes or something. And so after doing this iteration, just a few times, we can have a large amount of what we're looking for, and we can test for it. So what I'm going to do now is show you how electrical engineering can specifically build this kind of temperature cycling machine using a few components, and you could do PCR very inexpensively. So how do you do this in electrical engineering? Well, really with computers and sensors and actuators. So let's think of like a computer. I'm going to call this a microcontroller. So I'll say it's a MUC here, like that, little microcontroller. It's like a tiny computer. You can find these, they're like Arduinos and things like that. And this little microcontroller has inputs and it has outputs, right? So it can output something, like think of your phone outputting a signal like a speaker. Would make sound, or it has inputs like think of your phone might have a microphone that's recording your voice, right? So these are your inputs and outputs. The output, though, is going to be some signal to tell a heater if it needs to get hot or cold. So we're going to apply some kind of heating block, and attached to it, we're going to have a sensor that just tells you, it's like a thermometer, and it's just digitally going to send back to the microcontroller, hey, if we're too hot, the microcontroller is going to decrease the output so that the heater gets cooler. If it's too cold, then the microcontroller is going to output a signal that's going to make this heater a little bit warmer. And the idea would be there's some sort of DNA sample that we can put inside of here to test, right? So, so all this is done with electronics. Let's first talk about how do you not only heat something but cool something. That ends up being kind of difficult. Well, your first thought of how to maybe heat your sample might be, let me take apart like a glue gun or soldering iron or something. Let me take apart something that gets hot and control the voltage or the electrical signals that go to that device. And what you'll find is, well, it gets really hot really easily, but how do I make it cold after that? And that's a little bit harder. Maybe we can put it in a bucket of ice, or maybe we can blow air across it or something. Well, there's a little bit more sophisticated way of doing that, and that's what really most PCR machines use, is something called a Peltier device. It's after someone who discovered it named Peltier. Peltier device. And these are interesting. They're basically these electrical structures that have, you see all these N's and P's. These are called basically p-n junctions. This is what's typically inside of a diode. If you're interested in electronics, you would learn more about diodes. But it turns out if you were to make diodes, which are kind of like valves for electricity, specifically current, and where they basically act like switches one way but not the other. Well, if you make those out of very specific materials, then they exhibit something called the thermoelectric effect, which is interesting. Meaning, if I were to put a potential difference, which is like a voltage, like a wall outlet or something, if I put a plus voltage here and a minus voltage here, on this other plate, then what's going to happen is one side will get really hot while the other side gets really cold, right? And if I were to flip that voltage, then the other side would get hot while the last side would get cold. So I can actually control if maybe, this very top side here, if it's going to get hot and cold. Now that's a little bit more sophisticated approach, because now we can heat or cool something all with one device. So you'll find that this is really what is inside of most commercial PCR machines. It's something called a Peltier device. It's basically these fancy diodes that exhibit a peculiar characteristic that one side will get hot and the other side will get cold when you apply a voltage to them. And then you can flip those, and we'll be using that to our advantage to make a system get to a specific heat level, like some temperature, and then we will make that temperature try to stay exactly where we want it to be. So if we want to be able to control these Peltier devices, we want to do that using kind of some brains for our whole project. And that's going to be a microcontroller. So this is something, for example, might be an Arduino. This is a very inexpensive, is about $20, sometimes less, a $20 computer that, we can give it a USB connection and have our computer code it and then remove our USB connection, and this thing will just do its thing. It will just do whatever we tell it to. It's got these signals that come out. These signals basically, unfortunately, are going to be referenced such that they only have basically 0 to 5 volts. And we'll find that our Peltier device needs to see a positive reference, but also a negative reference too. So we'll have to come up with another part to go on top of that. So this is an Arduino. It's very simple to code, and I would highly encourage you to, if you have an interest, buy one of these and or something like it, and get started in a project that you're excited about. You could build something that makes music. You could build something that tests for COVID. You could do whatever you wanted. The sky is the limit. You could build cameras. You can build whatever you'd like, and the time is now to get started, because it's never been less expensive than it is currently. So let's talk a little bit about how we're going to get the limited 0 to 5 volts to flip-flop a voltage back and forth on our Peltier device. So how do we fix this problem that we have a 0 to 5 volt signal that we could send out, and we would like to be able to send out something that's all the way from maybe plus 15 to 0 to minus 15. We'd like to be able to reverse the voltage so that not only do we have a higher voltage, but maybe we can go both ways. Well, the HBridge is what's going to do that, and it cleverly uses a couple of switches. You'll find this in motors. This is what we're going to treat as a Peltier device, is called M. But the reason it's called M is because you'll find these in robots too, and you'll see them as motors in automotives or things like that, electric cars. Especially RC cars and things like that would have like an HBridge in them. And let's say that this is going to be maybe plus and minus 15 volts, something kind of large here, something like 15 volts, which is a hobbyist. If you're doing plus or minus 5, 15 is 3 times bigger, so we'll say that's kind of big. So what's happening here is if we used our microcontroller to close switch 1 and to close switch 4, then we would see in this first case that this motor or Peltier device gets a plus here and a minus here. Basically, we'll just draw a line straight down. So it sees a plus and minus voltage that way. But notice, if we were to now open those switches again and close the other 2 switches, so we're now closing S2, and we're going to close S3. What would happen we would now see a plus here, and we would see a minus here, right? So we're able to swap the voltage that this device right here sees by either turning on these 2 switches or those 2 switches. In actuality, those switches are transistors. They actually look maybe like MOSFETs is what they're called. And there's kind of a rich subject area where you can learn more about these. But these are usually MOSFETs. And notice that maybe we don't want to put it all the way at 15 or minus 15 volts, the full heating. That's the idea of something called pulse width modulation, where maybe we just tap every so slightly, once in a while, we would tap the switches to be on part of the time, but not the whole time. So, if we had a signal that looked like this right here, notice there's a lot of dead space. Well, the average sometimes is 5, which means that sometimes it might be 15 or minus 15 being applied. the average of the dead space to the amount of space that's being used by 5 volts would basically give you some effective voltage level that's lower. So we can use this idea of pulse width modulation sometimes just called, it says pulse width modulation. I think I'm too bright right here. Pulse width modulation, PWM, and HBridges to control, this could be a motor that you want your car to go faster, but then you want to go in reverse, and then you want to go to reverse really fast. Or we could make a quadcopter out of this, but in our case, we just want to heat and cool something using the Peltier device. All right, so here's a quick demo of an open loop heating and cooling system that might be used to amplify DNA in like a PCR machine. So here is a sample holder, like a little vial, where we would put our sample that we'd like to detect some DNA. Maybe that DNA is a virus or something like that. So it would be contained in this vial. We would put it down on our heat block, and then this heat block is thermally attached to a Peltier device with a thermal compound, similar to you would use on like a CPU for a desktop machine or something like that. Now it's connected with these wires. There'll be some positive voltage, and then we would like to flip that voltage. When it's positive, maybe the block gets hotter and hotter. When we flip it, it becomes negative. Then this side of the block gets colder and colder. So one side gets hot, the other side gets cold. We flip the voltage, the top side gets cold, the other side gets hot. That's achieved by this HBridge here. That's a couple of switches that we hook up, and it's going to a much higher voltage and higher current power supply, but it's being controlled by this inexpensive Arduino computer that's got kind of a homemade shield that's just got a few things soldered on it. Now, we're programming this Arduino with a little bit of code. So this code is, there's a lot of tutorials, but it's really simple. There's not a lot to it. And we just are going to heat the block by giving it some maximum value and indicating we're doing that with a red LED light. And we'll hold that for like 4 seconds or something like that. And then we're going to go to some higher value and we'll just maintain that higher temperature value, and we'll indicate that we're trying to maintain a higher temperature value with a red LED and a green LED simultaneously. That kind of shows up on our video, but I'll indicate it through audio. We'll hold that for 15 seconds. And then we would like to cool down the temperature of the block. So what we would do is reverse the PWM to reverse the voltage. So we're telling the HBridge, the Arduino is telling HBridge to switch the voltage. And when we do that and we flip it, we're going to indicate that we're cooling down the block with a blue LED, and we'll do that for 5 seconds. Then we want to maintain some cooler temperature, and that means that we've got some low PWM value, and then we'll indicate that we're holding that lower temperature with a blue LED and a green LED, and we'll hold that for like a full minute, like 60 seconds or something, and then we'll just iterate that again. So each time we would be going through this loop, theoretically we would be doubling the amount of DNA present in our sample. And this is kind of indicated by this temperature sensor here. This is open loop. If you wanted to do a better job, you would have the microcontroller actually sense the block, but that doesn't make for a good demo at the moment. So right now I'm just indicating the temperature using this display right here. And it's a little bit laggy, so it doesn't tell us the correct temperature always, but we kind of get the idea. So we're kind of maintaining a lower temperature. I'll try to use another indicator as well, if you can see that. It's more like 54 degrees on the block. And it's because this is like a non-contact measurement. So if I can hold it straight, I get a measurement of 55, 54 degrees. And that's what is being held there at the block. And we'll see after a minute of holding at this lower temperature, we will ramp up by having a much higher PWM and flipping the voltage, and I'll try to indicate that here with we'll wait for it. So we're at 54 degrees, and we'll watch it kind of ramp up whenever the LED turns red. That means we're giving it, here we go. So we should watch it ramp up. It's at 60, 89 degrees. And then we're just going to hold it at 87, 86. It's going to hold it more at like 86 degrees. Why is this temperature sensor moving so slowly? Well, it's because it's contacting. Oh, now we're going to cool down. We'll watch it rapidly cool back down to 50 degrees or something like that. So this one uses a laser and a sensor, so it doesn't actually touch our heat block. This one actually has got a little bit of metal that actually has some thermal mass. It's got to heat and cool. So this is a loose kind of demonstration of how you could use a handful of parts to do something like multiply DNA, and I'm quite literally doing this in my garage at the moment. So you could do this or something like it as well. Similarly, we could have built a robot that moves around using an HBridge and a microcontroller, something like that. So I hope that you've enjoyed it, and take care.